Okay, let me actually jump back to the material that we had been covering from the last lecture. So we introduced tensors, and as I said, tensors are a generalization of the physical quantities that you already know, scalars and vectors, and the next natural extension to that is tensors. What are tensors? Physical quantities that act on vectors to give you other vectors. And this is a concept that I would like to make sure that everyone understands. Uh, it's I think somebody asked last time that scalars have magnitude, vectors have magnitude and direction. What do tensors have, right? So, for example, here, tensors are associated with two vector spaces. One space of vectors is the space shown by these red arrows. Vectors are represented with arrows. So if you think about all of the arbitrary vectors in this red space of vectors, that's one vector space. And a particular tensor will take each and every one of those pointy arrows, infinitely many of those, and the tensor will take a particular arrow to a different arrow in the blue space. Okay, so I showed you last time that this dark arrow went to this dark blue arrow. All the other arrows are similarly mapped from one vector space to another vector space. And an example of this is something that you've seen before, stress tensor, for example. A stress tensor, if you think about, let's say, a deformable body. Here's my deformable body. So if I have, say, a structure, a beam, and it has deformed in a certain way, then we know for sure that the bottom chords are in tension, the top chords are in compression, and if you go to a particular point, you can imagine the stresses at that point. That stress is a tensor. It's not just force over area. Actually, that we'll see later on that force over distributed force over area is actually something called traction. And what stress is a tensor, and if you look at stress at a particular point, what it does is it takes a direction vector, a unit direction vector, it acts upon the unit direction vector, and it gives you traction. It gives you force divided by unit area. So, so in the same way, a general tensor, some tensor will take one space of vectors to another space of vectors. And so it's not associated with a particular direction itself. It takes all possible directions to some new possible directions. Okay. So the best way to visualize, or one of the possible ways to visualize a tensor is this blue ellipsoid. It takes all a sphere of red arrows to this blue ellipsoid of arrows. And last time I was telling you that the natural way to represent a tensor in components is through these 9 components, because when a tensor T acts on some vector U, which has 3 components, gives you V in other 3 components, what this operation can be represented with is a matrix of 3 cross 3 components, 9 components. And as you remember, stress components, indeed, there are 9 components for stress, right? In general, this operation can also be written in a compact form. So if you were to write this operation in a compact form, you would write it as V. On the right hand side, I'm getting some component Vi. It could be V1, V2, V3. On the left hand side, what should I have? How can I write a compact indicial notation for this? T, Tij, Tij, Vj, right? Sorry, Uj. Tij, Uj. That's right. So, and of course, since J is repeated, that immediately implies that there is a summation sign here, but I will
intentionally not write it this time because now I want to start using the initial notation. So the fact that I've written this expression in this way means that there is a summation sign here, but I'm not going to explicitly write it. And of course, you can see that this follows all the rules. J is repeated twice, so it's a dummy index. You could replace, dummy means you can replace J with anything you want except I, but J could be K, L, M, whatever the meaning does not change. I, on the other hand, is a free index. It occurs exactly once on both sides of the equation, right? So if you were to expand this, you would get these three equations right here. And that's why this compact way of writing represents either this set of matrix equations or these three set of equations. So it helps us to write in a shorthand compact way, okay? Bless you. All right, so that's just a brief introduction of what a tensor is. We'll get into much more details about properties of tensors and whatnot. Quick thing to point out before we do that is similar to a scalar field. Remember we talked about temperature fields over a body. A vector field. Can anybody give me an example of what a vector field might be? Velocity of an object or a deformable body. So for example, this guy, if it's flexing and moving, then each and every point in the body has possibly a different velocity. So a velocity field looks like a bunch of arrows of different lengths and pointing in different ways over the extent of a body. In the same way, we have something called tensor fields. And as you might imagine, for example, the stress and strain. Stress and strain are not uniform in a deformed body. From different points and different points in the body will have different stress and strain. So if you think about that concept, then tensors also occur as fields, which means that at each point in the body, for a scalar field, you had a signal magnitude, like a temperature associated with it. For vector fields, at each point of the body, you had an arrow, a velocity of that particular point associated with it. For a tensor field, at each point, at a particular point, you have an ellipsoid associated with it. So if you can imagine, in each point in the body, you have ellipsoids associated at that point. So it's kind of a complicated picture, but that's what a tensor field would look like. What I'm plotting here, for example, is this again, that bracket with the loading the bottom half and fixed on the left hand. Most often visualizing that tensor field as a bunch of ellipsoids, different ellipsoids at different points is kind of messy. So what we do is we pick out certain key components out of that ellipsoid. For example, say stress, if we represent it with sigma, then sigma xx or sigma yy or something called von Mises stresses. Those are all scalar fields. So scalar fields can be represented with a color. Right? If I have, for example, temperature is a scalar field. If I draw temperature as a scalar field, then red areas could be hot, blue areas could be cold temperature. In the same way, if you pick a specific component of a tensor, one of those 9 components or some other measure, scalar measure of that, you can plot that as a color map over the entire body. So that's one way to visualize a tensor field. If you can imagine, if you have 9 components, if you were to plot all the 9 different components on 9 different maps, that would be one way to visualize the tensor field. But essentially what a tensor is, it is a map between one vector space to another. One of the possible ways to represent it is an ellipsoid. So if you think of a bunch of ellipsoid at different points, that's what we are talking about, is a tensor field. And believe it or not, we will have to work a lot with tensor fields because our bodies or structures that we're talking about are going to deform. They will have different stress and strain tensors at different points, and we are going to have to do a lot of operations on these types of tensor fields as we go on. Okay. Couple of notational things as well. We are going to represent a tensor field as a tensor T associated with a point X, kind of like a function of point X. This does not mean that T is acting on X. Okay. A tensor field, a tensor T acts on a set of vectors U at that point. So if you think of, let's say, a velocity field, if you associate each and every point of that body with a particular arrow, a velocity, then some tensor could be acting on that velocity vector at that point and giving you another vector at that point. At a different point, again you have a velocity, a different tensor could be acting on it and giving you another vector. So when we write T as a function of X, we are referring to a tensor field, as opposed to as opposed to the tensor operation, which means that the tensor T acts on vector U to give me another vector V, or more precisely, we should write it like this: that tensor T at a point X and acts on a vector U at a point X to give me a vector V at a point X. So we'll talk about these stress and strain fields in chapters 2 and 3 when we deal with deformations. But for now, we just need to understand what is the difference between an operation of tensor acting on a vector U and tensor being a function of the position X. Okay. All right. So let's take a look at a few properties of these tensors. First thing, a tensor is a linear operator, which means that when a tensor acts on some vector, the quantity here in parentheses is a vector, what we'll get is alpha times T acting on U plus beta times T acting on V. You can verify that. T times U will be a vector. Alpha times that vector would be another vector. Similarly, T times V will be a vector, and scalar beta multiplying that. So the right hand side is a vector, the left hand side is a vector. This is just a property of linearity. Tensors can be added and subtracted together. What does that physically mean? That if you think of a tensor as an ellipsoid, one tensor is T, another tensor S is a different ellipsoid. If I add both of them together, then you need to think of two different ellipsoids which comprise of all these arrows. So if I take these two blue ellipsoids and add them together, what I'm essentially doing is taking one arrow out of that blue ellipsoid, another corresponding arrow from another blue ellipsoid, doing vector addition on those two, and getting the result that way. Okay, that operation is simply represented with this: the tensor T plus S acting on U distributes over this vector U. So I would write it as tensor T acting on U plus tensor S acting on U. So tensors can be added and subtracted, and their operation is simply represented by how it acts on a particular vector. Scalar multiplication, no surprises there. Alpha times a tensor T. Can anybody think of a way to represent this new tensor, alpha times T? If a tensor is represented by an ellipsoid filled with these blue arrows, what would alpha times T represent? A bigger or a smaller ellipsoid depending on the value of alpha. Yes, indeed, we are talking about how the resulting ellipsoid, the blue ellipsoid, would look like. So alpha times T of U, and those are some basic properties. We can also generate tensors by doing what is called a dyadic product. So of two vectors. So So up until now, we had talked about vector products, where we had looked at scalar multiplication, dot product, and cross product, right? And a scalar triple product of vectors. Now I'm talking about how to combine two vectors to give you a tensor. So for example, we could write a tensor T as the dyadic product, which is represented by this, U dyad V. What does that look like, or what does that tensor do? The best way to understand that is, but the best way to understand any tensor is to understand how it operates upon a set of vectors U to give me another set of vectors V. Okay, that's the only thing that defines a tensor. The two sets of vectors U and V. That's what defines a tensor. So let's see. In this case, if T is some vector U dyad with V, the way that vector will act, the way a tensor will act upon a new vector W is defined as, when I write these three triple lines, that means defined as that operation is defined as the dot product of these two vectors, U and W. So I'll write that here first, V dot with W, and what's remaining is U. What's remaining is this U that comes out here. So the result of the tensor operation, the result of this tensor operation T acting on W is a vector. So as it should be, because a tensor T acting on a vector W gives me another vector V dot W, which is a scalar, times a vector. So that's how this dyadic product is defined, without reference to any coordinate system. But if we do work with components in a specific coordinate system, there is a easy way to understand this. A tensor T, which can be represented by U dyad V, acts upon W in this way. So we'll write U as a vertical 3x1 components, vector V as horizontal, and let me ask you, what is the product of a 3x1 with a 1x3? That would indeed be a 3x3 matrix. And so if you express T as U dyad V, the components of T will be 9 components given by the outer product of these two vectors. So the way that this operates is, you can, since this is all matrix vector operations, you can change the order of multiplication. You can multiply V and W first. What would be the product of a 1x3 times a 3x1? 1x1, a scalar, right? What would that scalar be? V dot W, right? That's exactly what V dot W is. So V dot W, that gives me a scalar. What I'm left with is this vector U. So I'll write that as VI WI, and remaining thing is U1, U2, U3. So so that's one way to visualize this in components. Another way to write the same thing is, if I write this as, so let me ask you this, can I write this is T right here, this is T, can I say that T acting on W is equal to all of this? Essentially, I'm asking you, can I say that if I pick all of this, can I say that is this equality valid? Can I say this? Why or why not? So on the left hand side, what do we have? A tensor acting on a vector to give me a vector. On the right hand side, what do we have? I have a 3 cross 1 matrix really. This is not a vector because it's just 3 numbers. It's not referring to any, there's a coordinate system involved in these 3 numbers. So indeed I cannot write that as, I cannot say that the tensor T acting on vector W is this. What I can say is VI, WI, and then I can say UJ, EJ. Is that right? So all I'm doing is V dot W, this quantity in the parenthesis, which is the same quantity here, V dot W. What I'm left with is U. The vector U can be represented as UJ, EJ. Since EJ is a set of unit vectors, this equality now is valid, right? All right, so lots of these types of small properties and things that we'll use to learn about this initial notation as well. Another interesting thing is something called a tensor basis. You remember when we talked about vectors, we said we'll set up 3 basis vectors, E1, E2, E3, right? So in 3 dimensions, a particular vector can be expressed in terms of its basis vectors. E1, E2, E3 are basis vectors. The same way, a tensor can be expressed in terms of its basis tensors. There were basis vectors. There is something called a basis tensor. And the way that we generate these basis tensors are using this dyadic product. So, for example, if I have some, let me draw that. If I have some basis vectors E1, E2, E3, then I can use those basis vectors to generate a tensor basis. For vectors in 3 dimensions, I had 3 basis vectors. For tensors in 3 dimensions, how many basis tensors would I have? Tensors have 9 components. So each one of those components will be along a certain tensor basis. For example, in case of a vector, we had U1, U2, U3. U1 was along U1, along U2, along E2, and along E3. Each one of those were along basis vectors. So in the same way, if I have a tensor which is represented by these 9 components, each one of those components will be along a particular tensor basis. So the way we represent that is using this expression. We write the tensor components as T11 E1 dyad E1, and the way we represent that is with a matrix. So we have T11 E1 dyad E1 is referring to this 1 cross 1 position. E1 dyad E2 is referring to this 1 cross 2 position. T12, similarly T13, T21, T22, T23, T31, T32, and T33. So this is again a compact way of writing this long expression. But note here that I'm saying that the tensor T is equal to the first component in the first tensor basis, second component that basis, third component that basis, and so on for all the 9 components. Each and every one of those terms is a tensor. You add all of those 9 tensors to get the original tensor. The way we represent that, I cannot write an equal to here because these bunch of 9 numbers is not equal to the tensor. The tensor is represented by these bunch of 9 numbers. Okay. All right. In terms of components, how does a tensor act on a vector? We have this way of expressing that. So we can write that as Tij UK and EI dyad with EJ acting on EK. Can I rearrange all of these terms? Can I rearrange all of these terms like the way that I've done? I've just picked out Tij up here, UK, to get out of that summation. And now, indeed, I am using the summation convention because there are I is repeated, J is repeated, and K is repeated. So indeed, there is a triple sum sitting up here, right? And the operation between EJ dot EK, let me write it the other way, EJ dot EK, what is that? That is EJ dot EK is delta JK. And I'll should maybe write that out explicitly. So Tij UK delta JK and in the direction of EI. All I did here was to use the property of the dyadic product that we had talked about out here. When we have this type of an operation, tensor acting on a vector, the last two vectors dot with each other. So that's what I did here, EJ dot with EK in the direction of EI. So we write it like that. And now we can use the contraction property of delta. So we can possibly contract out K and replace that with J. So what we get is Tij Uj and in the direction EI. So T acting on a vector U is indeed the exact same expression that we had before as well, where we already saw that, but I'll write that again. Tij Uj Ei. There are I is repeated and J is repeated. So it means that there are two sums here, correct? And if we were to write that in an expanded way, what would that look like? Indeed, it would look like exactly what we had up here. It would look like these three equations with all of those 9 terms. So this is an important thing to note here, that maybe I'll actually write that here as well. For I equal to 1, we get this equation where J is being repeated, J equal to 1, J equal to 2, J equal to 3. Does it make sense? So that shorthand equation that we wrote for I equal to 1, we get the first equation where J is repeated, so it's being summed over. Similarly, for I equal to 2, we get the second equation. I equal to 3, we get the third equation. And in each of those cases, J is being repeated over 1 to 3. And that's exactly what we have here, Tij Uj. So as soon as you see that these two indices are the same, what this can be represented with is a matrix vector operation. This matrix vector operation, if you expand it out, looks like this. Right? So this is something that you'll have to start to recognize, that when I say Tij Uj, it's nothing but a matrix times a vector. Okay. All right. A couple of examples of tensors. We have an identity tensor. Identity tensor has, again, 9 components, where those components can be written in this form, delta ij ei dyad ej. Let me ask you this: how many terms does this represent? 9 terms, indeed. I have 2 indices, both of them are repeated. So for each value of I going from 1 to 3, for each value of j going from 1 to 3, I'll have all of these things. all of these numbers, delta ij. And the way to represent an identity tensor would be when I and j are same, we get ones. Those ones go on the diagonal. When I and j are not the same, for off diagonals, we get zeros. And indeed, an identity tensor is represented with an identity matrix. But an identity matrix is not a tensor. Okay. All right, another example of a projection tensor. What is a projection tensor in this particular case? It takes an arbitrary sphere of vectors. So for example, if I have, maybe if you think about that red sphere of vectors, we have, at that particular point, we have a bunch of infinitely many vectors. What this projection tensor is doing is taking a particular vector and projecting it onto this plane. Okay. So if you think about all of these possible vectors, all we are doing is kind of projecting them onto the plane the same way for the bottom tensors. And the result of all of this tensor operation is actually an ellipse in this case. It's not an ellipsoid, or it's a special case of an ellipsoid where really the third dimension is 0. Okay, so what we get for this particular projection tensor is take any arbitrary vector and project it down to this plane with a normal of n. The way we can write this projection tensor is using an identity tensor minus n dyad n. So I'm claiming that this particular tensor, when it acts upon an arbitrary vector u, will give me a vector v, which will be the projection of that vector u onto that plane. Can we check that? Let's see if that works. How would I do that? I'll just take the tensor and see how it acts on an arbitrary vector. That's what defines a tensor, right? So I acting on u minus n dyad n acting on u, and these two vectors get dotted with each other, so dot product there. I times, or the tensor I acting on u, what does that give me? U itself minus these two dot products, so I get u dot with n and in the direction of n, correct? That n goes out here. So can we physically interpret what this is? Let me ask you this. What is u dot n? Right. All the perpendicular vectors to that. So what is u dot n? Right. U dot n is a vector that is in the direction of this normal vector to this plane. So if I have any vector u, u dot n would capture the component of that vector in the direction of n. If I take all of that entire projection in the direction of n, subtract it from the original vector, what I would be left with would be this vector in the plane of that, in that plane, right? So that's exactly what's happening. That's how this projection tensor works. I expressed it in the form of a tensor and checked its operation on an arbitrary vector u that gave me the mapped vector v, which was always in the plane. So this is an example of how a tensor acts on a vector. Any questions on these things? Question? Yeah, go ahead.
I'm a bit confused about the matrix notation of tensors.
Okay, let's see. This one?
No,
Above that?
about this matrix notation. Now,
Here?
if you consider the product of the first two vector, what we can say, first column vector and row vector, column, it will give us a scalar product.
No, it would give you a 3 cross 3 matrix, right? So 3 cross 1 times 1 cross 3 will give this. That's why I called it an outer product. So if I have a vertical vector and a horizontal vector, if I do matrix multiplication on this, then I would get these 9 components where the first one would be U1, V1, U2, V2, U1, V2, and so on. So it would be a 3 cross 3 here, right? Okay. All right. So let's see. We don't have a lot of time left, but might just be enough to cover a couple more properties of these tensor properties of tensors. So there is something called a tensor composition, which means that which means what I've been talking about up until now, like a tensor acts on a vector u to give you another vector v. There could be yet another tensor that could be acting on v to give you another tensor w, another vector w. So what this means is that on the original vector u, there is a sequence of 2 tensors acting. First, t acts upon it to give you v, then maybe some s acts upon it to give you w. Okay, and this operation is called tensor composition, and indeed it can be of a tensor composition can be of 2 or more possible tensors. So, for example, here I'm showing you that I'll construct a tensor R by composing 2 tensors S and T. How does that work? I'll first compute T acting on U. We know how that works. It takes a red sphere to a blue ellipsoid. Then once I have that blue ellipsoid, a new tensor S will act on that blue ellipsoid to take you to another bluer ellipsoid. So the way that we represent that with components, I have the original operation T acting on U. That would be represented as TKLUL times EK. Does that make sense? That's this, the quantity in the parenthesis here. I'm writing that as TKLEK. Can we check if that's true first of all? Did we talk about this on the previous page right here? We said that T acting on U is TIJ UJ EI. Can I change arbitrarily? Can I say that instead of IJ I'm going to use what was it? KL. So can I say it is KL times L and K here, EK? Can I say that? Yes, because both I and J are repeated, which means they're dummy indices. Like you can replace them with anything. Why? Because indeed, since they're repeated, there are 2 summation signs, sum over I and sum over J. What variable you use to sum is immaterial. Right? So indeed, what we have here is exactly the same as this. And then on the left-hand side of that, I have this tensor S, which I'm writing in the tensor basis, Sij, Ej, dyad Ei, dyad Ej. This entire thing is the tensor S. This entire thing is the tensor U acting, tensor T acting on the vector U. If I try to simplify that, and then we are done. So if I simplify that, we can write this as Sij TKL UL EI dyad with EJ acting on EK. I'm going to take the dot product of these two because that's how tensor acts on a vector. That gives me delta JK. Write that out. I get Sij TKL UL delta JK EK. I'll contract out K, replace that with J, and what we get here, sorry, I have 3 Ks floating around. I made a mistake somewhere. Oh yes, thank you. So it should be EI. So I'm contracting out K, so I'll contract this one out here and call it I. And that means what I have is Sij Til U, no, Til Ul, and in the direction of, sorry, again, it should be J. TJL UL in the direction EI. The whole point was, can you think about what this operation is? What is SIJTJL? So I'll leave you with a thought, and if you think about that, what you should have is a matrix S, a matrix T, and if I look at Sij and Tjl, what we are really doing is a matrix multiplication of their components. So tensor composition is represented with their matrix multiplication. Okay. All right. So let me stop here. I've already gone way beyond, and I'll see you back on Friday.